flaws of some commercial devices also. One indium arsenide and one silicon in class. Then we discussed how uh, adding an intrinsic layer of some width can help us, and how avalanche photodetector are used, and what are the use cases for avalanche photodetectors. Then we discussed some concepts regarding direct detection, uh, where we introduced the concept of noise in photodetectors, both thermal noise and shock noise. And dark current is a concept we introduced. So basically, any unwanted signal will be noise. So if some light is leaking into your link and you're getting some photodetector current, even when no signal is coming falling on the photodetector. In that case, we have to consider the dark current also. And then we briefly touched upon these two concepts: noise equivalent power and detectivity. And we don't usually encounter these quantities, but you might see them in future. So noise equivalent power gives us what is the signal power required for SNR equal to 1. And then we discuss coherent detection. Not much in this, but we introduce the basic concepts, like how a local oscillator, which is basically another optical source, will be added to the input signal, how that can affect SNR, how the detection happens, things like that. Although we introduce these signals as time-dependent signals, during this week we kept considering a constant signal power in most cases. So even though we are talking about this on-off-keying kind of cases, when we're talking about this SNR and all these things, we're talking about only when power is on or off, like we are not going averaging over each sequence. I think ma'am touched it in class also. These are some of the formulae that were introduced, like what is the photocurrent, how is the photocurrent related to input power, input optical power, then how quantum efficiency is defined in this case, how number of photons incident, how number of electron-hole pairs are generated, how those two quantities are related. Then we also related it to how absorption can be related to this quantum efficiency. If we assume everything is going towards generating electron-hole pairs, then bandwidth and time constants that were introduced briefly. Then APD's multiplication factor was introduced, and then we went ahead and discussed this noise variance, how short noise is following Poisson distribution, but we approximated using Gaussian. For Poisson distributions, mean and variance are same. When they are both large, we can approximate it safely using Gaussian distribution. And we introduced the concept of SNR and how local oscillator intensity is current change. And here, I just wanted to show you briefly how the photodetectors are captured in the MATLAB code. So this is the same program as the last time we showed this fiber how to model. This was the main takeaway from last time. And here we are making a function, our own defined function that takes some electric field, responsivity and load resistance values, and this what is the receiver bandwidth. Then it does how to simulate this short noise and thermal noise in a simulation such as this. What we do is we find the expected current as this responsivity times optical power, which is again approximated using this electric field intensity squared. Actually, electric field squared gives you intensity, and when you integrate intensity over some area, that gives you this optical power. So power and intensity we usually use it interchangeably in this optical communication. But know that although power is proportional to this electric field intensity, there is some intricacies we're ignoring. What the spot size, what kind of intensity, what kind of mode are you expecting? Those kind of details will enter here. There will be some concept. So basically, we go with this expected current we find. Then for thermal noise, we can find the variance using these expressions we have. OKT, RL, and then we basically generate a random variable that is following some distribution. So this rand n function generates a normal random variable, and we multiply it using this square root of variance into standard deviation. So multiplying with that, we will give you this whole expression will give you a random variable that follows the required probability density distribution. Similar thing we do with short noise. Find a variable and find a random number that captures this random part. And ultimately what you will get is this sum of all three contributions. And to convert current to voltage, in our circuit, it will be 3 times 1. Then we go ahead. You see some noise in the output oscillation. That's all I wanted to say. Can I move ahead if there are no questions?
And you have any doubt on this MATLAB or that simulation part of photodetector, how it work? Please unmute yourself and ask questions.
And MATLAB I will try to share as soon as possible. I have to add these comments to the variable. Last one is in MATLAB part or what?
Jagannath, can you mute yourself and whatever you have doubt, can you ask? Jagannath,
Yes, sir. Hello.
So, how do you uh, simulate a random noise that is added to your current?
Yes, at that moment you are not audible properly. There's some network slowly, so that I am not
Okay,
clear this
okay.
part.
So, is this readable, by the way? Is this too small? I don't know how to change that.
Yes, sir, it is readable.
So, to simulate the noise effects, this thermal noise and shock noise, their variances are known to us. So, how do you generate the noise signals themselves? Because here we're going like sample by sample, we go, we add some uh, white Gaussian noise, which is basically a normal random variable, which is the easiest way to simulate this additive white Gaussian noise. So we find the noise variance that is expected, and then add the normal random to each of the samples. So this is where these intricacies are coming. Normal random variable of some dimensions, because here this input electric field is has multiple samples. This function is handling all of the samples. So we will generate normal random variables to make sure those normal random variables have the correct variance. I multiply this normal random variable by its standard deviation, which is square root of its variance. So this whole expression will generate a normal signal, a normally distributed random signal, and we will assign it as thermal noise term. Similarly, we will repeat the soft noise term. The total current you will get is the current you should have gotten because of the optical power input, plus this thermal noise term and the soft noise term. And the rest of the code takes this, so we are multiplying load resistance. Clear? For changing case, I think slightly lower is also allowed. I think we will touch it in next week.
So I have one doubt. Can I ask right now?
Yes.
So if cladding is not available, if the cladding is air, so does the communication is possible or not?
It should be possible.
So how come?
Why not? Cladding needs to be some lower refractive index to allow for total internet reflection. That's all.
Then why we are using cladding?
It protects the thing, protects the fiber. Also, it's controlled.
So sir, if we don't use the cladding, then also it will work now.
Yeah, it's not just cladding. They will have some protective layers on top of it also. And cladding, uh, I think around 125 micrometers in diameter. Your fiber core is just single mode fiber core is just uh, 2.5 to 3 micrometers. Uh, no, 5 to 6 micrometer in diameter, 2.5 to 3 in radius. So it's very
Also, it
thin, very weak. So
also it helps in dispersion reduction also.
yes, yes.
Any other questions regarding
And for
MATLAB or
10 gig, for 10 Gbps transmission, I think 5 gigahertz is also enough. We'll get some distortion, but 5 gigahertz seems to be enough. As the
Practically,
device.
we can use we can use optical fiber without cladding.
yes,
It
Namita?
will be tight,
Actually,
like it won't be mechanically like strong.
Okay.
actually, we need to protect the fiber through the environmental effects. There is a surrounding effects is lot of like the temperatures, air, and everything, and it will damage the fiber. It will not. The data will be transmitted without the cladding, but we need to protect the fiber for long time term, and up to some data will be not lost in case of the cladding. That's why it is necessary. Without fiber you can send the data. For short distance is possible. For long distance you need a cladding of the fiber to protect it.
Okay, sir. Okay, sir.
Anything else? Please unmute yourself and please ask a doubt. I think we have only 13 to 14 students, and everyone should be unmute and ask and
Excuse me, sir.
part. Yes, Abhishek.
Sir, the final exam which will be held will be MCQ based or subjective.
MCQ, because it will be evaluated by NPTEL team, not by us. So it will have to be MCQ based. Something that can be auto graded, similar to what you're doing in the
Okay, sir.
weekly quiz.
Thank you, sir.
That's why this class is important for you, because the exam is the MCQ based, and it's question will be based on the basic of that. So if you not participate and do not ask the doubt, then it will be trouble for you in the exam also.
Sir, in optical fiber communication, noise is added only from the receiver section. Na? Even the channel and transmitter does not play any role in the addition of noise in the system.
No, no. On when we have transmitted the signal, that time we maybe the noise will be added in that case also during the transmission also that. It not
But
on the
sir,
receiver side.
in the lectures, in the ma'am lectures, it was told that only the noise will be coming from the receiver section only. The optical fiber communication channel will not produce any kind of noise.
We yes, it is correct. But in the receiver side we have to detect that noise, because in the transmitter side we cannot identify what the signal the noise will be contained in that case. And it receiver have also created a noise, but in some cases during the transmission the noise will be added in that case also, not every cases, right, Jonek?
So we are just going by OK kind of thing. So
So
this
whenever there is
transmitter
a
will have phase noise can be there in laser, but for OK we ignore the phase parts. The receiver will add the most of the noise. Also, next week we will see that this amplifiers will also add some noise. Those are the primary sources. Is that okay?
Kushagra, Kushagra, are you there? Harshita. Yes, Jagannath. Lakshmi, Kushagra. So, Jonex, should I go? Should I
Yeah, yeah,
continue?
yeah.
So, please unmute yourself and answer that questions for discussion for me and you. So, what do you mean by the photo detector? Anyone?
Photodetector converts the optical signal to the light signal, and
Optical
the
signal
major
to light signal?
optical signal to electrical signal, optical to electrical conversion.
Okay.
And the working principle photodetector is basically based on the depletion width on the photon applied on the depletion width of the diode, and from that we can calculate the responsivity, which is equal to output electrical current divided by input optical power.
Okay. So, working principle, it what? It will work on the forward bias, reverse bias, or whatever
Reverse
the
bias, reverse biased.
and whatever the condition of the that light will be fall that so it will be detect that light any condition that electrical condition satisfy that condition.
So the light should be fall on onto the depletion region.
No, if the any condition that if the any material like that there is a amorphous like that silicon germanium or like that and they that material will
Sir,
be
it depends on the band gap, exact band gap.
oh, okay, band gap. So band gap should be greater than equal to how we can that if the band gap is less
Uh, Sir, there is a three
1.24.
condition. I think band gap, the energy, there is a transition that will takes place in the three different possibilities. The
okay.
energy must be equal to h nu, greater than or less than h nu. That is the
Okay,
energy of the.
okay, okay, good, good. Anyone apart from that Jagannath and Namita? Anyone want to add something? So, what is the performance parameter of photo detector, Namita or
Sir, first of all, the performance parameter is responsivity.
okay? So, what is the responsivity?
Responsivity, it is the ratio of IP by P naught,
Okay.
PN, or optical power P naught sometimes.
So, what is the
And
IP?
if IP is the output electrical current divided by the input optical power.
Okay.
Uh, Sir, it is highly sensitive and independent of the temperature.
So, photo detectors will not depend upon that temperature.
No, sir.
Its
It
performance
should be the
less.
requirement.
Okay. Another performance parameter apart from responsivity. So, what is unit of responsivity?
Amperes per watt.
Good, good. And other performance parameter, Kusagra?
Response time.
Bandwidth,
Response time.
This is
So, how you define the
express
response
electric
time?
field.
so it's bandwidth.
Band gap is the performance
Yes,
parameter.
bandwidth.
Bandwidth, okay, bandwidth, okay. So, Kusagar, can you elaborate that response time? How can you define the?
It depends upon the transient response and the RC times constant. They should be low
Yes, it's
for
depend on the two parameter, but how can you define the response time? If I say that this response time is 13 second, 14 second, or in the millisecond, microsecond, so how you can calculate that response time?
Sir, it depends upon what kind of photo detector we are using. Either we are using a simple PN junction, PN photodiode, or a EIN photodiode. So in EIN photodiode, as the depletion width of the intrinsic region is larger, so the carriers move with the drift velocity, so the response time is less.
So suppose that yes, somehow correct. I will explain that. Like that, this is the I and T graph. This is the our baseline, like the dark current. We have not exposed any light on the material. When we have exposed on the light, it will go like this curve, and it will saturate after some time. And when we remove that light, it will come again to our baseline. So whatever the response time, this is the my maximum current will be come due to the exposure of light, and this is the my base dark current ID. Okay. So response time is defined as that transient response or rise time from that taken from 10% to 90% of the maximum value of the response. So it will be we calculate like that maximum response is like that my 5 microampere, and this ID like that my 2 microampere. Okay. So whatever the 10% of the 5 microampere, it is around 5 into 10, but it is around 0.5. Okay. And what is the 90%? It is 4.5. So 0.5 to 4.5, it will take, we calculate the time. So it is our response time, that from the 10% of the response to 90% of the response, how much time it will take. So it will be a response time. Again we have to calculate a recovery time. What are the photodetector will time taken by from 90% to 10%. It will again come to down for 90% to 10%. Then we have to calculate this is the recovery time. So what we require to design the photodetector, or if we use the photodetector in our optical communications to detect that light, it have a less response time and less recovery time. It is the best because it will detect the light in the microsecond and millisecond or in nanosecond. This photodetector will be best quality. So this will be the response time and recovery time. Any question on this? Anything? Another performance parameter? Anyone else know that? Apart from responsivity, what we can calculate in photodetector?
Sir, quantum efficiency may be
Yes,
required.
quantum efficiency is the important parameter. So how you define the quantum efficiency?
Sir, it is the ratio of electron generation rate and to the photon incident rate.
So ratio of the electron generation rate upon photon incidence rate.
Yes, sir.
Okay, and what is the unit of that? Efficiency
Actually,
have,
not sir.
Hello.
Actually, not all the not each and every photon incident on the depletion layer will generate electron hole pair. So
yes.
that's why we are calculating the quantum efficiency.
So how that will, what is the significance of the that quantum efficiency? So
We
what
can
is
calculate we can
yeah,
calculate how much current is generated by the incident
Sir,
photon.
sir, it can give a particular cutoff wavelength.
what?
Sir, a cutoff wavelength so that we can find a suitable band gap
So responsivity is my IP beta Q. 1 minute.
divided by input by H.
That quantum IP beta kin upon Pn by Hv. So IP is the current generated, and this is the charge of the electron. Due to one electron, how much the current will be generated upon that power of that incident light. This is the HV wavelength of light, and this is the Planck constant is the constant, and V is the wavelength of light. So it will signifies that our material or photodetector is how much efficient, that if generated, if we incident one light on that like 365 nanometer, 500 nanometer, or that whole visible whole spectrum of the light, so it will how much the electron will be generated due to that light on that material. So if we have the higher quantum efficiency, it means it will be generated more number of the electron per unit of the incident of light. If it will be generated less, quantum efficiency less, means this photodetector is bad quality, and we cannot detect but predict that whatever the electron will be generated due to light or some external biasing voltage or whatever that we have to apply. So that's why the quantum efficiency signify that how much the efficient of the photodetector to generate of that convert that optical signal into electrical signal. Okay. Any another parameter you can remember that after that responsivity, quantum efficiency, bandwidth, response time.
Sir, absorption.
Absorption.
Yes, sir. Absorption of material.
So absorption will be generate what? Yes, absorption will be signify that how much the light will be absorbed on the material that. So due to
Yes.
that, if the absorption coefficient is large, then it will be generate more hole and electron pair. So anyone can tell me the relations between absorption and responsivity?
Sir, power absorption by power input is equal to 1 minus e to the power minus alpha by alpha
Okay.
w. I think this is the relation.
Is the responsivity equal to 1 minus e की power minus alpha w is the deflection width into lambda,
Yes, sir.
and it is 1.24 is the Eg, it is band here there, that electron that h and q we multiply, then it will become 1.24 like that. It is constant that you read one Eg equation equal to one band gap, we remember that 1.24 upon lambda. So it is q and something will become hv and Planck constant, and we measure, then it will constant 1.24 will become.
Sir, repeat it. 1 upon 2 4. What is the formula?
This band gap we have to measure of the that you show that whatever the band gap of the material should be, hv should be greater than equal to eg, that condition for the photodetector.
Yes.
So we measure the eg value from h and v, that Planck constant, and that eg we measure in the electron volt, and h v Planck constant, v equal to c by lambda. So c equal to 3 into 10 to the power 8, and Planck constant is equal to 1.6 into the through which
Okay.
that 1.24 will become. Okay.
Okay, sir.
So this is the that Namita told that we have the depletion layer, and when exposed the light, electron and hole pair will be generated, and it will reverse bias. So when the light will fall on the junction, it will generate electron and hole pair. It will on the depletion with electron and hole pair will be generated here. So why photodiode is work under the reverse bias? Why cannot we use in the forward bias? Any reason?
Sir,
Anyone?
because we have to collect the electrons and holes which are generated in the depletion layer. That's why we are reverse biasing it so that we can collect it.
So it's like that electron have negative charge and hole have positive charge. Okay. So when we given the negative bias, it means it will reflect that electron and it will attract the holes only. So
The barrier
Yes.
height.
So barrier height will also increased.
depletion width will increase or barrier height of that? This one you should tell about that. What happened that case? Why we use the reverse bias? I can apply the forward bias positive voltage, and it will also biasing will be, so it will reduce the barrier height or increase the barrier height.
forward biasing will reduce the barrier height.
Okay. So if it will reduce the barrier height, then electron will be easily go to the collector side. Like that we have this P and N, and it will have to biasing like that. And there is a electron and hole pair, there is a hole and it will come here only, that generated. Then if you apply a reverse bias, it will become on this path. The electron and hole will become on this path side. And it may be that attack the positive side also. It is the diode function, basic diode function. So photodetector is also the diode, like avalanche photodiode we have, pin photodiode, PIN photodiode, Zener photodiode, Schottky photodiode. There is a lot of type of the photodiode, photo multiplier, photo tube. So why we use the reverse bias? So what is the dark current? Can you anyone explain about a dark current? What is the significance of the dark current in the photodetector?
So when the photon light is not applied on the depletion layer, then the current generated is basically a dark current.
So it should dark current. What is the significance of a dark current? It should be useful for photo detector. How much it affect the property of the photo detector? If our dark current will be high or less, more or it
It
might.
should be effective for photo effective move.
Yeah.
Hello.
Yes. Yes.
Sir, there is a fractional change in the diode current due to reverse bias, and the photo effect is more measurable and in a particular band gap. Sir.
Suppose I have I dark and it should be greater, large, or I dark it should be less. Whatever requirement of photo detector, dark current should be required great or less. Namita, suppose Mano we have not exposed any light and we have to do the biasing of that device and we have to reverse bias. In that case, whatever the generation of the current should be large or less.
Please pardon once again.
Suppose that this is our device and now light will be not focused on our device. This is replacement with W, this is P and N, and we have applied that reverse bias around the junction and we have not exposed on light. In this condition, the current travel through that diode, it will be less in the reverse bias condition or great. It will come in nanoampere, microampere, milliampere in that
Sir,
case.
it is in the range of sir, microampere.
Of the reverse current
Yes, sir.
in the microampere.
Yes, sir.
Yes, sir.
Yeah, have you think that semiconductor will be give the reverse current in the microampere
So yes, sir. Yes, sir.
in the reverse bias condition?
Yes,
Yes.
sir.
If my characteristic like that of the
Yes.
diode characteristic like that, sorry.
Sir, there is a diffusion layer.
So this current will be in a microampere or this will be, you think that this is the reverse bias condition, my? Anyone apart from Namita? So dark current should be good for the any photo detector or it is bad current? If we have the large dark, then the performance of photo detector will be good or not? I just want that answer.
It is bad.
It is bad. So why it is
Sir, it
bad?
is necessary. Sir, it is necessary to have this dark current.
It is necessary. It will be there be dark current. Like that responsivity we may have to measure like that already with that IP beta P in. And we can also measure that IP minus ID dark and P in. If you think that this will be in the microampere, in like that 100 microampere, it is in a 10 microampere, then what is the responsivity in that case?
Responsibility will decrease in this case.
So means dark current will reduce the responsivity, and for any photo detector we require the high responsivity.
Yes, sir.
So it will not, if we have the large dark current, then what if our every parameter, that quantum efficiency will be decreased, responsivity will decrease, it will take more electron and hole pair will generate, take more time, rise time, response time, every parameter will be affected due to that.
So yes,
That's
sir. As in the lecture, it was told that there is a trade-off between responsibility and bandwidth.
yes.
So I think that's why, sir.
So we required a photo detector for less dark current. For any device, this is dark current like that. We have not applied anything on this. We just biasing like that 2 volt or 1 volt, and it will just give the current. Okay. Anything with just material, it will be not useful for us, because we have to detect the light, and the current will be generated when the light will be detected, because due to that the light only. Like there is in the semiconductor we have the diffusion and drift. Have you, anyone explained the diffusion and drift? What is diffusion and whatever drift current?
Sir, drift current, it is the flow of current through the material or device under the influence of applied electric field intensity.
Okay.
And diffusion is basically due to the concentration gradient difference.
So diffusion is due to only the material only.
Concentration gradient difference,
Yes.
sir.
So concentration is whatever that concentration of that hole and electron.
Yes, sir.
It is
Yes, sir.
intensing or
Yes, sir.
extensing only.
Yes, sir.
Yes, sir. It
And
is.
drift is in the influence of the electric field. We have to external field apply. We have outside through that. So whatever the exposure of the light will be like that due to the, we have the exposure of the light here on the, this is like the material, and like the drift will become like that only, this current, this is the drift. We have the Vx and dx, we have to calculate everything. And diffusion is like that, we have I equal to I drift and plus I diffusion. We require we require a less drift current. Electric field is generated by itself of that material only. If we apply the high voltage, it will have the more power loss in that case. It will have the more resistance due to that generator of electric field, and it will not useful for us. So power loss will be greater in that case if our drift current will be more in that case. So we require less power on that. It will operate for the less power. Generation of the power or losses of the power should be less. Now industry will be work on the cell power. Our device should be work on the 0 volt or 0.1 volt, 0.2 volt, 0.3 volt. How much your the voltage of your mobile? Any electron device, how much voltage take to operate?
4 volt.
Yeah.
0,
If
0 to 4.
what is the cut-in voltage of silicon? Anyone can answer? Cut-in voltage of silicon or germanium?
0.7
Yeah.
for silicon.
What?
0.7 for silicon. 0.7 for silicon. 0.3 for germanium.
Okay. So means to operate a silicon device like that, this is the diode, our silicon diode, it is the characteristic, and after that it will generate, means after that zero point 0.7 electron volt or 0.5 electron volt, means if we applied a voltage of 0.7 or 0.5, our device will be given a start to the current. So how much the lower voltage we have given that, so it will operating, after that our device will be start to conductive, giving the current like that. So whatever that, anything will be due to diffusion only that. So a photodiode usually in the reverse bias condition, because change in the reverse current through the photodiode due to the change in the light flux can be, as the reverse saturated current is directly proportional to light flux. Now in the reverse bias PN junction, the width of depletion region is be increased. Like that, this depletion will be increased in that case. In the forward bias, it will be it will be decrease, and in the reverse bias it will be increase. So can you give the relation between depletion rate width and that reverse bias and forward bias? Have you read the equation of the diode? How depletion width will be depend on that reverse bias and forward bias? Have you remember this equation? Have you read in BTech or MTech? Have you remember this equation?
Yes, sir.
So it will be
Yes, sir.
square
Yes,
root
sir.
of directly proportional square root of the VBI, or V naught minus VF, any one reverse that forward bias minus reverse bias, someone writing like that. This is reverse bias voltage. Okay. Some person will be written that V naught minus VBI, someone may be noted like that. So it will be directly proportional to square root of the VBI. So if the reverse bias voltage will be more, then depletion will be increased in that case. Then what will happen that? So by applying the dial voltage, mode of the incident photon convert into electric current, or the efficiency increase as long you make sure that the leakage current remain the minimum level. So we require less minimum current. We never need the electric current should be generated devices should be more. So on the other, when you forward bias APN junction, the width of depletion will be reduced, so only a small portion of incident photon get convert into the electrical current. So what will happen in that depletion region? There will be more number of electron and hole pair will be generated if the width will be more in that case, and it will generate more number of electron and hole pair. If the width will less, it will generate less electron and hole pair, and whatever the current will be get output, it will very less in that case. And whatever in that case we have more I dark current and less I photon current. So we need to generate more number of the electron and hole pair generation. If the electron and what you said that previously that if contact efficiency is the number of the electrons generate per unit of the incident light. Okay, so if you get the more number, our exposure area should be more in that case. Then that's in that case only electron and hole pair will be generated more. Any doubt or anyone have you understand or not that? Please respond.
Yes, sir.
Yes,
So
sir. Clear,
so
sir.
so that's why we have required a in the reverse bias junction. Some like that avalanche photodiode have some multiplication property that one electron will be multiply and generated electron and hole pair. We some type of photodiode like that P and IN photodiode we use that in insulator we have to increase that width, we have make that one insulator layer in between that junction. So to improve the performance of the photo detector like that responsivity, quantum efficiency, bandwidth, gain, signal to noise ratio, all are the performance of the photo detector, rejection ratio. So we need to require a more number of electron and hole pair generation in that case. Some photodiode will be working on that photo getting effect, photoconductive effect, photovoltaic effect. So there are different mechanism of the photo detector depend upon that of the material of that device, how much like that contact you have to taken, like that you have to make the Schottky contact, ohmic contact. It is metal semiconductor metal type of the photo detector. It's depend upon that your design and that material and type of the photo detector, and you have to decide that forward bias or reverse bias. But standard photo detector will be work on the reverse bias only. So I have already explained that equation 2 epsilon by q, but so rise time have I already defined, and someone also that given that the rise time depend upon the two that. So how can you calculate the RC time constant? Anyone else?
Time taken to range from 10% to 90% of the maximum output.
So, someone select that Jagannath told that depend upon that RC. So, if our resistance and capacitance of is increase, then our response time will be decrease. Okay, it will be inversely proportional on the
Yes,
time.
sir.
So that V naught equal to V naught 1 minus 1 upon, this is the equation to calculate that output voltage. So rise time equal to log 9 of RC, or like that 2.2 RC, that uh, we have taken the log value of that in that V naught beta V naught, and that time constant, and some T we have to define that standard T, like this T, not that T, this T, time taken by the photodetector to response, that saturation or that, this is T. So this is total rise time of that T RC plus T transient. What is T transient time? Transient time. What is
W
transient
upon
time?
V trip.
Yeah. What is transient time? Namita?
Sir, I forgot. I think transit time is a time taken by the charge carriers to cross the depletion layer and to cross the uh, P and N side of the junction of the
Yes.
diode.
Yes. So how much the time taken by the electron and hole pair to cross the depletion layer? Like that time taken by from valence band to conduction band, electron will take, that is the transient time. Okay. If you in the semiconductor, there is a one is the conduction band, there is a valence band, and between that this is the EG, our band gap. So that from electron hole pair will be generated and we reach in the conduction band, and there we have to collect from the conduction band only. So it time taken by that T tangent. So mention the source of noise in the photodetector. Anyone can explain what is the source of noise in photodetector? What type of a noise in the photodetector? I previously explained that question also, that noise we have to discuss on the first class and between that class also. What type of a noise will be in the photodetector? Hello? Sorry, this is due to the net. Again, I have to join. Sorry. Yes, I am listening. Anyone can answer that noise. What type of the noise? So, what is the source of thermal noise?
Sir, I really forgot right now.
Temperature.
Okay. So source of noise in a photodetector is the thermal noise and the short noise. Thermal noise is due to the random motion of the charge in the passive component. Like that, charge will be moving some like that, this charge, this charge, this charge, and it will be interact and collide, and after that it will generate some heat, and due to this it will be create the noise in that replacement layer. So it will be like the white Gaussian noise. Can explain anyone think that what is the white Gaussian noise? What is the spectrum of white Gaussian noise? Anyone remember that?
So it is maybe by PD by 2 and not.
What are?
It's a P by 2 and not maybe.
Like I talked about a spectrum of like that white noise. How can you in the graph that explain that white noise? So it will cover all the this is like that. It covered all this area, whole area like that, white color area like that. We spectrum like that. White noise is like that. In the short noise, the photon arrives at the random instant, and hence the at the arrival time of that photon, it will generate a short type of noise. So it is stationary. It will not randomly. And one is that due to the dark current, some noise will be generated. So short noise is uncertainty in the arrival of photon caused by the quantization nature of the light. So like that, some photon will be reach a time, some will be some less time, some will be less. That's why this is the short noise. Like that, you have read the quantization we have in the communication. We have to step to do the quantization of that. Some quantization step size and that to in the communication. In the like that in the photo detector, the light will be focused on that photodiode, and it will generate electron and hole pair on the receiver side. Some will be reach it fast, and some will be less slow, and due to that the noise will be generated. It is a short noise. What is the dark current? Dark current noise. So dark current already said that there is a maybe that some photo detector is there, and I have focused like 365 nanometer of light. If anyhow some ambient noise will be fall on that photo detector, like that air no, some light of that atmosphere and will be fall on that, so it will generate some disturbance in that signal of the 365 nanometer light, or due to the some external electric field, or it will generate more dark current. So this will be due to that generated disturbance of the signal is due to the dark current, we have to refer that. So this will be also some type of noise we have to consider in that photo detector. So we have to minimize all these three at the receiver and in the receiver side. So if we have the less noise in the receiver, we can detect that input of signal accurately in that case. Anything questions on this? Any questions? My voice is audible? Hello?
Yes, sir. Yes, sir. Yes, sir. You are
Yes, sir.
audible.
Yes, sir. Audible.
So anything on that noise, because this is important, you have assignment on that, that's 4 to 5 question on that noise also that. And maybe 1 to 2, 3 question will become on your final exam that also. So
So the
thermal noise,
last assignment was the very tougher one. Last assignment, not this one. Last assignment was a tougher one.
yes. So thermal noise we have to explain that for kbt
K
by pl
KBT RL into RL
into
RL.
fn into delta f. This is the thermal noise variation. So Kb is the Boltzmann constant, T is the temperature, that PL is that this is RL, sorry. So RL is the effective load resistant, delta F is the bandwidth, and Fn is the noise figure corresponding to whatever the noise figure of that, through which we measure the variance of that thermal noise. The square of sigma is the variance of that thermal noise, we can measure that.
Can you repeat the last one?
This Fn is that noise figure. Figure of merit, we have to define that now. F out by Fn, that figure of merit of any signal. So we have the one some constant of that noise figure on that, in that case in the thermal noise, like that white Gaussian type, or that and how can you define that short noise? Any formula, anyone remember that?
Two Q I D into
Yeah,
RL. Two Q I D into RL.
2qid
Into RL.
into RL. So if the load resistance will be more, then there will be short resistance, short noise will be more.
Yes, sir.
So how can you minimize that load resistance?
So it is connecting nearby to the reverse bias. It is external to the circuit. So we can take a lower value of RL.
Okay. So what is the SNR, signal to noise ratio? Anyone can explain that? Apart from Jagannath and Namita, there are 4 or 5 students. I think other left that. So signal to noise ratio is defined as like that. Ratio of the signal power upon ratio of noise power. So in photo detector we require the high signal to noise ratio. For that we require the less noise power. So any photo detector is required high signal to noise ratio in that case. So it will define as that IC square into R upon sigma square into R. So this is measure the average power of that signal, and the power will be written in that case in that RD is the resistance of the photo detector, in and product of that signal power, sorry, that signal power is the ratio of that photo detector and input power, resistance of that photo detector, and whatever the input power of that light, through this we measure the signal power. So how can we reduce the thermal noise? Any method? Anyone can suggest any method, one or two, that through which can reduce the thermal noise?
By increasing load resistance.
By increase the load resistance, okay. Other than, we can reduce the temperature, control the heating of the receiver electronic circuit. We can reduce the noise figure of the amplifier, that we use that to amplify the signal, that input signal. We can optimize the bandwidth, so it will not generate, the random path will be less in that case and generate the less thermal noise. What is that operation regime? Operating regime? Operating regime. So the signal to noise ratio that I already explained that this is the formula. This is the method to reduce the thermal noise. So we have the two operating regime in that photo detector. One is the thermal operating regime and another is the short noise operating regime. So when the optical power is high, it is the short noise because that depend upon previously I have explained that uh, due to that more optical power that part travel by the electron and hole pair, some will be less, some will be more, and when the contribution due to the thermal noise dominates, it is called a thermal noise. It is a condition that the short noise should be always greater than the thermal noise we have to taken. So we have not required a thermal noise, we have to reduce the thermal. If the short noise will be there in that photo detector, we can this is the classical limit of that thermal noise, but the short noise is the fundamental limitation because short noise will be generated due to the light only, and it will be generated due to that material, maybe due to the operational temperatures, output bandwidth of that amplifier and that other parameter. But this will be due to that depend upon the light intensity only. This, so this is a fundamental limitation, and we should be reduce this. This is some assignment questions. If you want, then I will explain or I should leave it.
Yes, sir. You explain. You can explain.
So I think that you can answer that also, that the quantum efficiency you have to given that input power of that photon 6 into 10 to the power 6 generated at wavelength lambda, you have to given 300 nanometer, and Eg have to given that generated electron, that electron and hole pair generated will be like that 3.9 into 10 to the power 6, and quantum efficiency you will already define that IPH but a Q upon HV upon lambda, or number of the electron hole pair generated upon incident time. So electron hole pair you given 3.9 into 10 to the power 6, and incident power is 6 into 10 to the power 6. So you directly divide that and you get that quantum efficiency of photo detector. Okay? Have you understand? Namita, Jagannath, Harshita.
Yes, sir.
Yes, sir. Yes, sir. I got it. I got it.
Again, next question is what will be the range of the responsibility of the photo detector has the same value of the computer, whatever the previously we have to calculate the quantum efficiency is obtained for the question for wavelength range of, we have to calculate responsive for wavelength of the 1100 nanometer and responsivity for 1600 nanometer. For both we have to calculate different. So responsivity we have to define equal to IAP bata P in. Okay. So now you have to that quantum efficiency and P in have some relation. It will IP bata H bata generator of whole pair. From that you can P in generation. So this is the that responsivity measurement of the detector, that n lambda upon 1.24. So from that this is the quantum efficiency you calculate, lambda you have to given, and 1.24 is the band gap that you given that. So this you can calculate for that 1100 nanometer and 1600 nanometer. Consider a 1.5 micrometer receiver, that indium gallium arsenic type of photo detector you have to given. Here the electrical bandwidth of receiver will be 10 gigahertz and quantum efficiency you have to given. Diode current is 1 nanoampere, a load current is 1 kilo ohm. So receiver amplified noise to be negligible, and amplified noise will should be given earlier. So you have to estimate that noise current, and when the receiver is kept in the transmitter and having the output power of the 10 milliwatt. So anyone can tell the formula of that? How can you calculate short noise? That Q 2Q into. So responsivity you have to calculate through this. Short noise is this formula, that 2Q into RDPN plus ID delta F upon Fn. Okay. So Q is the electron charge, RD have you given, Pn you have to given, dark current you have to given, that receiver bandwidth delta F have you given, and that output power you have to given. Can you able to measure that? Can you calculate? Hello? From this equation you can calculate RD. Pn you have to given that input power is around whatever given that 10 milli. What will be the thermal noise current in the transmitter? And again you have to calculate thermal noise. So delta thermal have to be given that 4 upon load current you have to already given, and this is in the, so you have already was only that 4 but RL you have to divide the load current into this signal, that RL 10 kilo ohm you have to given, and this will become to that through this you can calculate thermal noise. Any doubt, anything apart from this? Any doubt in the assignment problem you have to given, like non-graded and graded type assignment? You need any hint or anything? I think Jonek have provided all the formula which is used to solve that assignment. So Jonek, should we stop?
Yeah, sure.
So Namita, have you any
Yes, sir.
doubt? Any doubts? Jagannath, Arshita?
Sir, not till now. Maybe in the by tomorrow, maybe I'll send you some questions, sir, on your email ID.
Okay, okay, no problem.
Okay, sir. Okay, sir.
Okay, thank you. So we meet on next
Thank you so
Tuesday.
much, sir. Thank you
So
so much, sir.
okay, thank you.
See you next week.